I remember, no, I flashed with you a while ago, no, or in the previous video or in the previous discussion that we have, no, about this torque, no, the idea of a torque. No? Now, torque is a concept, no, where a force, no, is acting on a body at a given distance. No? So when we try to apply that force, no, on a given distance, the product of that distance and the force, no, is what we term as torque. No? Now, the longer usually, no, the rod that we are using and the bigger is the force that we are applying, then that torque, no, could either be increased or decreased, no, depending on the length and the amount of the force that are being applied. No? So here is a concept again, no, of rotational motion. No? So this one, no, this propeller, so maybe you can call it as a propeller. We could have there a Ferris wheel. No? I don't know if you are if you really like riding in a Ferris wheel, no? But these are rotational motions. No? Now at some point there must be some forces that are involved here, no, to make this whole thing now rotate. But for this to rotate, there must be one fixed point, no, where the body cannot go away. No? So maybe now we call that fixed point at the center of this Ferris wheel, no, as its fulcrum. No? So the whole Ferris wheel will simply rotate about that point. No? So it cannot move up, down, no, left, right, but it will just simply spin around this point of rotation. No? Now the same is true for this propeller. No? So that propeller spins because maybe there are forces that are found or located, no, on the ends, or maybe, no, turning this. No? But this one is simply turning, no, on a fixed location again. No? So rotational motion. No? So rotational motion is a result of two forces that are moving, no, in two different directions. No? And it's continuously, no, causing the rotation there. No? So the idea of what we call a torque, no, is necessary, no, for us to understand it. No? So here, this triangle that we now have, no, is known as a point of rotation. So we term this now with several names. We call this fulcrum. No? And that fulcrum, no, when this bar, no, is being made to move, no, it has to be steady at that point, but maybe the other end of the rod will now make a, no, rotation. No? But this one, no, is steady in its place. No? So dira lang siya malibot. No? So again, no, we term it as a fulcrum. No? Now, on the other end of our rod, no, there must be a force here, no, to cause that given rotation. No? So there's a 50 Newton force present. No? And the rod that we have there, no, needs to, maybe, no, since you are pushing it downward, so this one now will cause a rotation that could probably, now we can consider it clockwise. No? So if you try to push this, no, so manaog ni sa, no, and then kung sige yun, magitulod na da, no, then it will now go down, no, and eventually you'll see a rotation that is probably, no, going in a clockwise manner. No? So what if we will apply the force in the other direction? So let's say we'll push it up, no? But we keep this steady. No? So the fulcrum will never go away, but this side is able to make a turn. No? So if you push this in the other direction, then another turning motion, no, or direction can occur. No? So if you push this up, this one will now go in the other direction. And you can describe the motion there as counter, no? Counterclockwise. No? So torques can create, no, clockwise or counterclockwise motions. No? So again, no, the rotational motion. No? So, but again, no, that is possible when you have a force, no, that is acting, no, on a given length. No? Now imagine if this force is placed. No? What if dirita siya ibutangin sa may point of rotation? No? Can the rod rotate if you apply the force in here? No? There is a may fulcrum. No? What do you think? No? Can rotation happen if you let this 50 Newton force pass here in this triangle? No? What do you think? The keyword again there, no, in this one, no, is torque. Again, torque is the product of the force that you apply, no, and we know, and we must know the length of this rod. No? So when you know those two values together, no, then you can have no a value of torque. No? Now again, in this illustration, what if we will have no a similar amount of force but in a much shorter distance? No? So it's now closer to the rotation point of rotation. No? So this one will still cause a rotation that is clockwise, no, ang FB. But since it's much closer, no, then maybe no, we could have here no a lesser torque for FB. No? So the effect of FB, since it has a shorter length, will have a lesser torque. No? FA, no, maskin parehas lang siyang force, but since this is farther no, from the point of rotation, the torque that results here will be much greater as well. No? So torque. No? So again, I think no, at point C, no, that's an impossible task. There's no distance anymore no, from the point of rotation. So the zero distance no, will result no, in a product equal to zero torque also. So since there's no torque at point C, that it's impossible to create a rotation anymore. No? So again, the values that we call as length. No? So this is what we call the fulcrum. Oh no, the moment arm. No? So ang LB or ang L sub A, no, the length from here to A no, is called as the moment arm no? Or the lever arm. No? So lever arm of A is longer than the lever arm of B. No? So the lever arm times the force gives you your torque. No? So these are the two things no, that are responsible for the value of the torque. No? Other books calls torque as the moment of a force. No? So let me just give you no, the key terms. No? So torque. So last time we used the symbol T no, for we used letter T last time for tension. No? But this time, no, we'll try to apply no, the word T no, for the word torque. So this is our torque. No? So what's the unit of torque eventually? So if force is in Newton and distance is in meter, no? So usually our unit for torque is Newton meter. No? So that's the product of a force times its distance. No? And when we went to our work energy concept, no, Newton meter, no, we equated it to the word joule no, last time. No? But this time, no, when we refer to torque, we will just call it as Newton meter. No? Let's just avoid using the word joule. Now, another word for torque is the word called moment no, of a force. No? Others would call it as the moment. No? Of a force. No? So they connote the same thing. So force times length no, is equals to your moment of a force. No? So ang moment na usually guys, it speaks about rotation. No? So that's why no, ining length nga ginahambal, di ba no? It is usually no, referred to as moment arm. No? Ang kalabaon niya halin sa point of rotation. No? So we have two directions for our torque, guys. No, one is clockwise, and one is counter, no, clockwise. No, now usually counterclockwise ang direction, no, just like when we deal with forces that goes left or downward. No, so kung counterclockwise, we indicate it by a negative value. No, counterclockwise. No, so meaning the clockwise rotation can be indicated as positive torques. No. So positive torque. Again, no, that simply shows our two varied directions for our no, torque. No? So positive torque when we deal with no, clockwise motion. So I hope you follow this. No? So negative for counterclockwise, no? And positive for our clockwise torque. No? Okay, so how can we make one object no, not rotate? Again, no, by satisfying no, the conditions for the second condition for equilibrium, no, wherein the clockwise and the counterclockwise torques are equal, no? Or when you add up all the clockwise and the counterclockwise torques, no? Their total value should be 0. No? So when they have a total value of 0, then the body will not have any, no, rotational motion at all. No? So in order for the rotational motion of a body not to change, no, the summation of the moment of a force or torque, no, which acts on a body, no, must be equal to 0. No? So duwa lang nga klase ang atong torque, no? Counterclockwise and clockwise, no, torque. No? So how do you get torque again? You multiply force times, we multiply our force, no, times our distance. No? Now we have here a uniform meter stick. No? So let's say we have a meter stick. A meter stick is how many centimeters long? Ang atong meter stick is 100 centimeters long. No? So ang atong ginobra, no, we position our meter stick, no, and balance it. No? So di ang balance point sa atong meter stick. No? So ang ining fulcrum naton, no, kung ibutang ta na siya sa 50th centimeter nga mark, no? Ito amo ni aton nga meter stick, 100 centimeters long na tanan. No? So kung dito siya ibutang ang aton fulcrum, no, sa 50 centimeter mark, no, then mabalance it na isa. No? Now that is assuming, of course, that the meter stick, no, is uniformly made. No? Parihas ang iyang kadamulon. No? All throughout, no, there's a uniform shape, no, of the meter stick. No? So again, a meter stick is 100 centimeters long. No? So these are the 10 centimeter distances, no, from one end ng 0 centimeter mark, no, hasta sa punta yung 100. No? Now, along the lengths of this meter stick, may ginpang position kita. No? We position a slotted weight. No? A slotted weight looks like this. No? So it's like a mass now with a certain hole in the middle. These are standard masses. No? So let's say we keep or have, no, 50 grams. No? We were able to gather 3, no, 50-gram masses. No? And we are to suspend it, no, in this following location. No? So pangitaon nato ng 14 centimeter mark. So 14 centimeter may be somewhere, no, in between 10 and 20. No? So we will be hanging one object here. No? Ang iya weight again is 50 grams. So 14. No? The next mark na ibutangan natin ang 32. So maybe 32 will be near to 30 rather than in 40 cm. So there are two masses here. And ang isa, no, is on the 58 centimeters. So after na di siya sa 50. No? Very near to 60. No? So may ara, tadi ka tatlong 50-gram mass. So duwa ka mass ang ara sa wala. Kag may isa di sa tuo. No? Do you think it will be balanced? No? Kung ipakabit nato ng masses. No? So ginpahang nato, no? Isa sa 14 cm, ang dason is sa 32, and ang isa sa 58, no? Do you think we will be able to balance the 3 masses here? No? Now what do you think?
Sir.
Maybe not, no? Maybe we need how many more mass? Most likely, no? If you want to find, no, and balance this whole thing, maybe we can add, no, one more mass on the right side. No? Now again, no, our goal is that, no, the torques that are caused by the weights on the left, no, ano nga klase rotation ang gina-create sa W1 and W2, no? Clockwise or counterclockwise? And what about W3? Now, what sorts of rotations are they creating? No? Okay, so we have here a process of balancing out. Now let us read the problem or situation there. No? Again, so a uniform meter stick is supported at its midpoint. No? So the midpoint of this meter stick is on the 50 centimeter mark. No? Now 3 50-gram weights, no, or slotted weights. No? So these are the metals. No? These are the masses that we place here. So 3 50-gram masses are placed on the following marks. No? 14 centimeter, 32 centimeter, 58 centimeter. No? And we want to add, no, another 40 grams, no, to be able to achieve equilibrium. No? So where will we place the last 40-gram weight. No? And question, what is the torque created by the 40-gram weight? No? So those are the two things that we want to find. So maybe now we will eventually find, first of all, the lever arm or the moment arm of W1. No? So when we get the lever arm, we cannot use the value 14 centimeter. No? 14 centimeter is measured from 0 up to here. No? Now the moment arm that we are trying to use for torque is always measured from the point of rotation to the location of the mass. No? So if this is 14 from 0 up to here, then if this is a total of 50 centimeter, minus 14, so 50 minus 14, L1 must be equal to 36 centimeter. So we will just subtract the value on the left, which is 14. Now for our L sub 2, L sub 2 is the value of W2 from the fulcrum. And L2 will be 50 minus 32 because this is the 32 centimeter mark already. So 50 minus 32, that gives us 18 centimeter value. Now, for our L3, L3 is of course going to the right already. But the lever arm there, or the moment arm, is still measured from the starting point, or from the fulcrum. So this is the 58 centimeter mark. So 58 minus 50. So because from here up to here is 50, so the length remaining is 58 minus 50. So it's only 8 centimeters. So using this moment arms or lever arms, we will try to find the torques that are created. So we have the following torques. T1 and T2, or the torques due to our weight 1 and weight 2, are both counterclockwise, so they are negative. And the torques due to W3 and the last torque W4, which is 40 grams, will be both clockwise, so they are both positive. So when you add all the negative torques and the positive torques, or the counterclockwise torques and the clockwise torques together, their total must be 0 because this one, what we want to achieve is a state of equilibrium. So that's why the torques there is equals to 0. So the product for our torque 1 is weight 1 times L1. For our torque 2 is the following as well. So how much is our weight 1? Weight 1, if you will not convert it to Newton anymore, and I think we will just use grams here. Grams will still be applicable. So we have 50 times 36, 50 times 18. So this is the lengths, and the mass. What you notice here is that I think now we made a mistake here for weight 4. Weight 4 should not be 40 grams, because what we use in our equation is also 50 grams. Now, kindly change this value here, so to 50. Kindly adapt 50, so that we will be consistent with our equation. So supposing we use all 4 masses to be the same, then the only last value there is the lever arm of weight 4. So weight 4 or torque 4 now will have a positive value because it is still clockwise rotation. So maybe somewhere here, dirito na siya ibaba. So all the negative values will probably be placed, or will be added together and combined to this value. So what we have now for our value. So our length actually that remains, so we will be placing the last value here, the last 50 grams at a distance of 40 centimeters from the starting point. So again, you can do the other process of multiplying it individually, and then solving for our L sub 4. So again, that's the length of our mass.